Thank you. Okay, thank you very much, and I hope you can still stand another talk with a little bit of complexity before lunch. I'll try to more briefly present the idea rather than too many technical details. And in addition, I would lead you into yet another extension to service orientation. We have heard extensions into security, privacy, theoretical background, semantics, and the basic idea is that you never use service orientation in isolation, but more or less in a software engineering context, and sometimes depending on characteristics of specific applications. We also saw, especially yesterday in the poster session, many interesting applications like music or fashion. And here's yet another application context, which happens to be production automation, with some different characteristics. I will talk about that. And the specific emphasis here, depending on that application area, is software evolution. I'll talk about later a bit more detail on what I mean with that. The background here is an ongoing research program rather than project in Germany, so-called Schwerpunktprogramm, priority program, in the software engineering area. It's basically the only software engineering coordinated program in Germany for many years. And it's on managed software evolution, whatever that is. And our specific project in this area is forever young production automation with active components. Okay, we come to that later on. Of course, there's many collaborators who did all the technical work, so I address them if you have technical questions. And what is specific in this program, this is like 8 groups, each group consisting of 2 parts. One system computer science group, thus in this project, and another application specialist group. And this happens to be the group of colleague Alexander Fay, luckily in Hamburg, so that reduces travel. And they concentrate on automation technology. Oops. So what is it about? The application area, production automation, was completely unknown for me as well. Has some interesting characteristic. It's a complex combination of hardware and software. We know it's called cyber physical systems. I'm looking forward to another talk about that tomorrow. The hardware is expensive and long-lasting. Traditionally, it was basically hardware-driven, but nowadays, you know, Industry 4.0, it's always a combination of hard and software. And the software has many functionalities, but also non-functional characteristics, and it includes services as well as workflows, as we would call it. And as we heard the other day here, you can also call the software mirror of this hardware system a digital twin. So what we try to aim at is to coordinate software and hardware in single systems, mostly automatically supported. So there are these toy systems. The colleagues in the automation area really have these systems. They are quite large, like a quarter of the Zoom or so. And they, I don't know whether you can see, it's like some toy production systems. They have some cranes, a conveyor belt, here's a crane. And they have some machines which do something to some products which are produced here, and the toy system is just stamping it somehow, and then it's moved from here to there, and in the end it's positioned in some place which is called magazine, some storage area. So this is, of course, a workflow. The whole system is providing a service, a product with functionalities, but also non-functional characteristics like how fast does it go, how much does it cost, how many failures occur, and so on. So that's the background. And then, of course, as these production systems are expensive and long-lasting, as I said, there are changes which occur occasionally. So these systems, part of the system may break, part of the system may be changed to improve the system or change specification of the product to be produced. And this basically is done on the hardware basic. And in many cases, it's forgotten, delayed, or whatever, not done correctly to mirror these changes in the software. So the aim is, the question is how to keep the software with both aspects, services as well as workflows, in sync with changing hardware components. So we want a coordinated development of hardware and software, mostly system support. And that's the aim of this project. Services in a real-world scenario should adapt to changes and do that more or less autonomously. I'll talk about that also. With respect to services and workflows, maybe they should detect changes automatically and then adapt to these changes. Well, it looks ambitious, it is, but it could be done, and some basic ideas are present how it could be done. So, the basic problem is we have challenges in the lifetime of such cyber-physical systems because we have different life cycles of the different parts of the system. The technical system first is designed, in the design and construction phase, then it's used, and then it's maybe improved by another design, and so on. And similarly, but in different cycles for the platform, which is the software system, and the software engineering cycles. And all these have their own time frame, and they are very uncoordinated. It looks like spaghetti, and that's the problem. We want to synchronize these things. And in practice, that's nearly not done at all. Amazingly, but it is. So if we sort that out, we have three different levels. We have the level of requirements of the system. What's the system going to do? Under which legislation, for which users, and so on. And in a long-lasting system, these requirements change over time. You start a simple system, then it gets more complex, and even more complex. I mean, this may be due to EU bureaucracy or whatever. I mean, that's the usual thing what happens during lifetime of a system. The software underneath starts nice and clearly, neatly, and then gets more complex, and with further addition is somehow a spaghetti structure of this software. And similarly with the hardware, maybe it starts with a single system and it evolves into a set of machines on which it is running and then ends up in the cloud somewhere. And all these things happen more or less independently. So I think you understand the problem we try to address. So, basic function of the system, we have a production plant, which has two parts, code and physics. Physics is the physical structure of the plant, and code is the software. And we have two aspects of it. We know that this is service orientation, what to do, the functional requirements, and how to do it, non-functional requirements. The problem is, over time, these things change. Changes of the functional requirements, please provide the product in a slightly different way. Result in changes in the production plant, which are easily done. The mechanics say, oh well, we change the system, it's easily, and it's now running and producing a different part. Fine, end of this story. No, that's wrong. Also, there's unforeseen incidents, like part of the machine breaks, and it's another part is put in place instead of the broken part, which is faster or more economical, and so on. What does it mean for the functional requirements? What does it mean for the non-functional requirements? hopefully doesn't produce a different system, but maybe produce it faster or cheaper or whatever. And all that has to be taken into account into the whole system, consisting of both parts, the physics and the code. So these changes result in changes here, and that influences the fulfillment of the requirements. Maybe we put a slower part instead of a faster part into the system, which makes the whole system slower. And that, of course, first changes the non-functional requirements, but in the end it may even change the functional requirement because some subpart is not provided in time in order to produce the overall composite product we end. Okay. So if we analyze what is happening there, we can still differentiate the three different levels. The informal requirements, that's what we think the system should do, in a way, a specified way of these requirements, and then we have underneath the technical side the software code and the physical plant. And first of all, they are all consistent. This represents the informal requirements, the code represents the formal requirements, and the machine executes the code. So there's no knowledge yet, this is all consistent. After a while the system evolves, and then the requirements change, the formal requirements should change accordingly, and the software code running on the machine. That would be nice. But in reality, as I said, sometimes there are new requirements. Oh, let's easily and fastly just build it into the hardware of the system. Forget about the formal requirements. That's not important. We do that later, and then we forget. So this is insufficient and leads to problems later on. And if we compare our specified requirements with what we really aim at, there's a so-called knowledge gap. In order to avoid that, we introduced another level, called model, of the system as an intermediate check. So this could be a way of formalizing the requirements. So what's the difference? The difference is that this model is able to, by itself, autonomously check the system underneath. Given some requirements, it's checking, it's testing the system. How many products do you produce in a given time frame? How costly is that? What is their characteristics? And if this is according to the model, everything is fine, but there may be changes. This is going slower than it's supposed to be. And then there could be two different choices. Either this change of the system is on purpose, was done on purpose. Maybe it should be faster. And maybe that's done on purpose, then it's fine, and the model has to be changed accordingly, or it's a mistake. So we first have to detect these changes according to the model, and then we have to evaluate somehow. Is it done on purpose or not?
Is this model maintained by humans, or is it maintained?
No, I come back to that later. Of course, that should be formalized in a way. Maybe Wolfgang would not completely agree, but formalized for us as practitioners in a way. And this should be part of the system and kept automatically. This is the main point, that this part of the model, the representation of the model, does these checks automatically and then contains the knowledge of the system. And then is able to compare it with the initial requirements, helping to evaluate whether that's purposely done or not. This could not be done automatically, the evaluation, but all the other things should be done automatically. So if we would do our pragmatic approach in this model, in this alternative, the model would detect there is something which it doesn't know about, so it checks with human intervention only here. Is this a change in the system or is it a mistake? And if it's a change in the system, the model should change accordingly. And if we do that, then we have the initial goal fulfilled, that the model, the formal model, represents what we really aim at. Okay. Basically, in this way, we have a runtime model, a model of our system. This is not really new, but the new thing is that over time these models change and adapt automatically based on detection and evaluation mechanism of the system underneath, based on learning after evaluation whether the system was changed or whether some mistakes occurred, and then adapting these models accordingly. Questions: how to preserve the available knowledge during evolution, how to keep the knowledge, how to manage the model. How can evolutionary changes be detected and evaluated at runtime? How to construct software that gathers this knowledge basically by observing the system. So in a part of this project we aim at methods and processes for knowledge carrying software in order to counteract aging. That now we should understand developing soft and hardware of a system in sync. Questions: how to gain this knowledge by available information without influencing the execution, by establishing documentation in some formal way. What is the reasonable meta model or software architecture for this knowledge carrying software in an external context? So this motivates the approach to generate scenario-based emulation of knowledge models based on low-level, in this production system, signal-level traces, test cases, which lead to traces of the system, which are then evaluated and modeled and represented in a so-called active component architecture. So basically we have three levels of representing the system itself, and especially changes to the system. We have the system here and we have event traces. This piece moved from here to there. This crane picked up this piece and moved to there. And maybe this piece after a certain while is still on a conveyor belt but not moving. These events and traces combined build a consistent system facade, a kind of low-level model of the system, and then have to be evaluated. Is this part of the model which we aim at, that things move through this production line from here to there and then are treated in some way? And when we evaluate that, we have a model at runtime. And as we say, runtime is long, maybe 10 years long. These models change, events happen, evolution happens, changes are detected, so that leads to models at runtime changing. And if we have such a model automatically built and kept in time, then we can analyze the model rather than the system, which is more difficult, in order to evaluate fulfillment of properties. Are enough goods produced in certain time? And in the overall project, coordinated program framework, there are different specific projects addressing certain parts of this process, like the acquisition of knowledge in a way from simple events, the build-up and maintainment of these models, and others of deriving from a model properties for functional and non-functional requirements, and evaluating whether these requirements are still valid in a given model after changes have occurred. I'll use this with 3 different colors in subsequent slides. So we have the event traces here, we have the evaluation of the events here, and then we have this deriving of meaningful statements like are requirements fulfilled at the end of this line. So in the first part we have sensors which sense the system and find and collect signals of the system state. These signals are interpreted in a way which then are meaningful pieces of information, which in the last step are combined into a machine state model and a so-called offline knowledge model, collection of knowledge about the system at a certain point of time, which then evolves as the system does over time. And based on that, we can make statements about the fulfillment of requirements in the system. So we start with simple data, we interpret them, we add some semantics to gain information, and then knowledge about the system in these three steps. This is the goal of the overall approach. So how to now, basically, your question, represent the knowledge about the model in some automatic way. So in this picture, we have the horizontal and vertical organization of a system with some parts and the whole system here. And then along this axis, we have the information abstraction. First, we have the physical, maybe cyber-physical system here. And then we have the first representation, which is one-to-one representing every single part of the system. Out of that, we could derive some knowledge about the system, some system's properties, and later on the requirements fulfillment as the user, as the application would expect from that system. How to represent that? We start with a low-level system, the hardware and the physical plant level code, and represent that in so-called knowledge-carrying software. So let's go and look what it looks like. It's confusing. It's a model consisting of, if you at least get something out of this picture, several components, as one could see here, one for each part of the system, which have some connection to the real systems by interpreting events so that they know what the actual status of the system is. When we interpret them, we can build out of these parts a so-called knowledge model, which with certain machine states, and which also does not just know about specific events, but also maybe the whole process, the workflow. This whole system executes, which aims at a certain, like producing some goods. So this may contain knowledge about the system state, knowledge about what the whole system is about, and maybe in addition, and that makes it more complex, even about the history of what happened before, and maybe what should happen in the future. This is what but history is easy. And then we have the evolution manager, which then knows the evolution steps of the system and keeps some management information about this changing knowledge models. Okay, so how do we represent these things? Some boxes, it always looks like boxes and arrows in between in computer science, but what do we do? In software development, we have many choices to represent things based on different development paradigms. This is more the tutorial part. There are nearly no students anymore, so we can pass it rather quickly. So there are different software development parts. We need an overall approach. This is called the software paradigm. And in history, we know there are different ones which determine the description and realization of software system at different levels of abstraction and historic concepts leading from imperative to object-oriented model. And let's look briefly at the choices we have. In the object-oriented paradigm, we have basically the objects which interrelate and which are based for method-oriented communication with client-server objects of governability and object identities and maybe migration of objects and so on. And we have some drawbacks of this approach, reusability, for instance, of objects, and we have some historic examples, we know that. Okay. More interesting and more along what we aim at is the component-oriented paradigm. Why more interesting? Because component-oriented software construction leads to the whole environment of supporting software development based on objects which are packaged into components in containers as coarse-grained units of application levels, self-contained with well-defined dependencies, and we have component repositories, so we don't really build software from scratch, but we combine existing components if at all possible. They're generally restricted to application logic, and the whole system doesn't exist yet because they're deployed. Okay. Examples are Java Beans, .NET, and so on. So this is interesting for software development approach. And then, of course, we have Solar. We all know about this. Services, rather coarse-grained services. I'm not talking about microservices. And coordination mechanisms with well-defined interfaces, synchronously or asynchronously, interoperability used based on standards. And we have all these existing examples. But in many cases, we want these components, services, whatever you call them, be a bit more independent, acting autonomously, setting goals for them and let them decide how to reach that goal. And that leads into the area of agents. Agents is a long-lasting tradition in computer science with many aspects. We treat agents here as a specific kind of components in order to develop software. That's a rather engineering-centered way of treating agents. We all know that there are others from artificial intelligence and so on. Communication with that agent is always asynchronous, message-based. Agent is a concept which uses sensors to sense their environment and effectors to influence environments. Agents make decisions autonomously. We interpret that in the right way. I mean, based on specification which they keep internally. Behavioral specifications with internal architecture, and then we have also this multi-agent systems which we can use, like Ulf did in his example, for instance, to represent a soccer game as a set of independent agents. Agent platforms exist in history, and we added another one in some recent years, which I come back to later. So if we look at these different software development paradigms, we have in different axes here modeling units from procedures to organizations and abstraction levels from static calls, asynchronous calls to rule-based programming of systems. And in the lower left corner, we could start with structured programming over object orientation, go to service orientation. And as we think, this is probably subjective, but it's our belief, we can go beyond by this agent orientation by adding this kind of autonomous behavior for specific application. It's not used everywhere, not necessary everywhere, but for specific application it does add some merit. If you look at these agent approaches, you have different sectors where agent could be used, from industry, commercial, entertainment, this is important, games, medical applications, or military. And then we have different classes how to use agents, multi-agent simulation, problem solving, this is more artificial intelligence, robot control, information management, or human-computer interface. And then we have all kinds of interesting combinations of these two axes, like, I don't know, household robots here, commercial application of robot control, or in the military environment, or in the medical environment, automatic operations. I don't know whether I trust it, but it's coming. And then we have logistics, that's interesting, in different areas. We have multi-agent systems in, look at gaming, entertainment applications. Or we have human-computer interfaces, avatars, as visual representation of agents underneath, and all kinds of these systems. And these agent systems, also including our own, have been used in many of these areas. Like we have done a project in logistics for hospitals, and we had some thesis applying agents for implementing games on different mobile devices and so on. Okay, I have some more examples on agent use. We can pass them fastly. Industry production, increasing efficiency of the production process. There are well-known examples of increasing the manufacturing of cars. We have used our own system together with Daimler for simulating production lines before they are actually built. They used to, when they build a new production line, that's a very long-lasting, very expensive process, you build some toy production line physically before, and that was still so expensive. So we introduced use of agent-based simulation instead, and that led to redundancy of a lot of physical example production plants and reduced cost. This also was supported by DFG. This was interesting. For logistics, we have many different areas. I mean, you can easily imagine using agents for production processes, delivering goods in real time, just setting the goals. These goods have to be delivered at that place at that time, and the agents care about, maybe in communication with each other, how to reach that goal. Interesting application area is also to govern the air traffic at a certain airport. Airplanes could communicate, or the air control could use agents to control planes. This has actually been done. Sounds dangerous if you don't trust the agent technology, but it works. And we have done that, as I said, like for hospital logistics. You have machines, you have people, you have patients in the hospital, and who is treated one by whom, by which machine, at what time, in an environment where everything changes whenever a new patient arrives. This is an interesting and challenging scenario in an earlier project, also a coordinated project together with other partners, like from medicine. We could prove that these agent-based optimization algorithms are better than traditional and still mostly used centralized approaches. Okay. Commercial applications, all kinds of electronic assistance for buying and negotiation processes. We know interesting other examples are some robots. We have bought a cleaning robot for our offices, not to clean them, but to learn about how to control such a physical machine by software based on agent technology. Computer games, as I said, very interesting. Maybe younger students know more than I do about computer games, but it's an interesting area to apply agent technology, certainly. And the challenging part about these games is not to develop a game, but to adapt the game to different hardware scenarios. And this could even be unified, based on the unified agent system software and military, of course, whether we like it or not, many applications of this technology. Yeah, and that's the end of the small overview of how to use and where to use agent technology. And if you believe in that, you can maybe understand our approach. We wanted to combine the marriage we have from augmented service-oriented computing and so-called service component architectures with the merits of agent technology. And that leads to so-called active components, which are agents covered under the, well, environment of the software component. So these agents internally behave like agents. They have a logic, they have a knowledge, they have a goals, they have a representation of implementations, how to reach goals. They sense information from the environment. They have a factor where they influence the environments. They have their properties. And this is interesting in the context I was using as an example here. They have internal knowledge about their environment. So an active component, as we define it, is an autonomous managed, potentially hierarchical, so they could be built into each other. entity that's capable of interacting with other active components in different modes, including message passing and method calls. So you can use different software engineering methods to program interactions of these components. And then there's an infrastructure and composing methods, invocation styles, and all kinds of internals of the active components, including what we use at services or workflows, and including knowledge of a certain kind. And for these agents, we need a certain platform, a system, software component which is able to let these agents run and execute. And this was done in the so-called JDEX. This is the based on Jade, completely new implementation for multi-agent systems in the first phase and active components in the second, where many of these kernel agents can run on a common kernel in a common system environment. And in a concrete application, we now can define active components as the application requires, and then have all the merits of letting them interact with others, keeping knowledge and intelligence internally, and still combine them in a way which we know from software engineering. So back to the example. Now we know what we use, what we use for implementing the system, and in order to represent it, we first have a direct mapping because the physical plant here, some overall system which happens to consist out of a magazine, a crane, it's always the same example, a stab and a conveyor belt. And this is in the first phase mirrored directly one-to-one by representational components in our active component system. And then we have added events which can happen to these components, which then are reacted on. We have encapsulation of local knowledge about this components. We keep knowledge here, for instance, about the current position of a crane, its way it can go. This is of course limited, and of all the other components as well, and combine that into a complete system. And then we can enrich it with a description of their functionalities at certain granularity levels. And then we can ask the system later on whether some requirements could be fulfilled by the system as the digital twin, the knowledge system, knows about the system. And in this phase, in sync with the actual status of the system. So we have a system representing observed physical plant parts, and in the system we have representations of the knowledge of the system, and then we have a so-called test case component which asks the system how many products are produced in a certain time span, what is the characteristic of these goods. If it doesn't change over time, it's boring. But it's not boring because it doesn't change. It's going faster, it's going slower, it's not going at all if something breaks, or it's going differently on purpose if we change the system underneath. And this could be tested and then could be checked again, as you remember probably, the uppermost level of our intended requirements of the overall system. And this could be done at runtime for the actual system state, what is the actual status of the system. But if we keep some kind of knowledge of the system internally here, we could also ask, is this time, how fast does the production process go comparably to what we had before? If it's better, it's fine. If it's worse, maybe it indicates a problem. And even more challenging, we didn't really do that yet, is based on what we can do and what we could do, we could even predict how the system could behave in the future. But this is still to be done. So we basically, on the lowest level, have our representation of the system, here consisting of the 4 parts. And some events, which can happen, like there is a workpiece ready, which was produced, and then we can interpret it at the next level, and then we can raise some exceptions if this violates, for instance, some of the intended requirements of the system. So at the lowest level, we have some signals which are already produced by the basic cyber-physical systems, which we just collect and then interpret. At the next level, we have the system behavior as represented as depicted in it. Some ask why, because it's easy, it's appropriate, and it could easily be machine represented. Of course, in our agent, we don't represent it as a graphic, but as a Java representation of the workflow which is happening. And then we can compare this workflow to the intended behavior of the system, and then again detect whether that's what we had in mind or whether it's a violation in a certain way. And if it's a violation, we again have to interpret if it's purposefully or is it a mistake. And doing this, we come from an observed process, timed events, learning them to different models which we adapt to when we interpret these events to new versions of the model in a cycle which we always follow in order to keep the software representing the state of the system on the one hand side and the physical or cyber-physical system in reality on the other. So in order to represent the system, we have for each, hard to read, this is again the 4 components of the system, an internal representation, what that component could do. I used the crane as an example. It could move from one place to another, maybe, or cannot do that, but just pick a piece, raise it up, maybe turn and place it someplace else. So it has a limited number of states which you can follow in a well-defined way, which we have formalization of, and then we can represent it in the digital representation in the component architecture of that component. And then we have an overall workflow of the whole system. And all of that is represented in agents. You cannot read this, but this is a picture of the agent system which represent all these components and their overall interaction in this JDEX-based active component system software. So in summary, we have a system which is observed from external, which is tested by test system, and based on that we gain some knowledge about the system which we keep in addition to the system itself. When the system changes, this knowledge about the system changes. This can be adapted to the change of the physical system when these changes are detected, and then these changes have to be, as I said, evaluated, and then derived from this knowledge, it has to be compared with the intended properties of the overall systems, and then the fulfillment of these properties, including functional and non-functional requirements, can be automatically tested. So we have our system here. This is the physical system. This is the representation. And this is the software active component representing this system. And then we learn from single events over interpreting these events and then comparing them with the requirement fulfillment, what that means for the overall system. So we have a running system, we have learned behavior of the system, we have extracted system properties, and then we have derived system knowledge based on engineering models, code of physics, and test cases, and this always goes in turn. When the system changes, we again run this cycle and change our representation of the system accordingly in sync with a real physical system. This was the first part, not of my talk, don't worry, of the project so far. It's only a few slides left. The rest is also just speculation. What could we do in the future? How could we extend this model? We call it linked fiber production automation. What if we could use, background is all these machines in reality are now, Industry 4.0, increasingly interconnected. And if we interconnect all these systems, and we have even problems on a single system to synchronize software and hardware of the system, and that's not easy, and we have to invent new things. What about using experience maybe other similar systems have at other places in the environment? So if this system is augmented, for instance, by some component in this way, and another system is augmented by another component in a different way, what if we have to build a new system augmenting this system by component in yet another way? Why can't we ask the other systems, do you have any experience? Have you had any similar cases, and how did you do it? What can I learn from it? And maybe this system offers his experience, this system offers his experience, and then we have this experience gathered from our system and still have to evaluate, is it helpful for our own context? If yes, we can use something. If not, we have to reinvent the wheel, whatever, if we have to do it in our own context. So this is the outlook. Wouldn't it be nice to have not only knowledge-carrying software, but also to share knowledge about beyond certain local solutions in local places. Connecting these systems, sharing information when systems evolve, maybe the same things, usually in certain application areas. The systems evolve to similar patterns, could be shared about beyond system boundaries to others. And then we could have even maybe an adjustment. Is this really the same problem as we have, or is it only nearly the same? And then we can, based on that, try to evaluate whether it's useful or not. But this is just pure speculation, no solution yet. Would be nice. Machine interpreted base of evolution knowledge. How can evolution relevant experience be captured? How can that capture the system context? How can evolution steps and their influence be related to our own system context? Under which condition is what happens to a different system applicable to ours? There's no experience yet. And this production automation colleagues, as I understand it, don't have any idea how to do it. Maybe we can help them, hopefully. Would be nice to then first of all start, when are systems similar, how can that be measured and expressed, and only for similar systems it would make sense to share experience. Can evolution steps of several systems be aggregated and tailored for a specific system? No one knows. Can evolution trends be recognized in cooperative evolution networks? That would be even better. We see that systems develop in a certain direction. What should we do to do that, and maybe do that earlier and better than competitors? That would be really interesting. Which methods are needed for proactive evolution recommendation? That would be the result of such a process. Proactive evolution recommendation. Pure speculation. Network evolution support platform. Again, of course, we don't want to just speculate how it could be done, but we are considering ourselves as engineers. Only thing that is useful if we are able to build a kind of knowledge evolution platform who at least automatically supports us in this process, as we did so far for the single local system. Okay, 5 minutes left, so I hope it's not too fast. For okay, conclusion is very brief. Whatever I said, we use services and workflows and varied applications, and added or included it into a software engineering context, use production automation as an example for a physical system which changes over time and use active components to implement that. So that's exactly it.
Questions, please.
So in the systems you described, the type of system you described, sometimes the requirements might span different areas. For example, there might be some temporal aspects of the requirements. Is it a bad question already?
No, it's good, but it's overly ambitious. I mean, we know that there could be everything, but if you look at these real systems, it's very basic, these requirements. Like produce so many products of this characteristic in this time, maybe under this budget constraints, and so on. It's very, very simple.
I was wondering how do you model this requirement? Because in runtime you have to verify it.
Okay, this process is not completely automatic. I mean, the system detects changes and produces maybe a summary of these changes, and then the human has to interpret whether that's meaningful, is purposely done or not, and then has to compare with the requirements. The utmost level of requirements, as I showed in this three-level picture, is informal and is not automatically supported. So the comparison of these change results at the most possible abstract level with the informal requirement has to be done by humans.
So in that scenario there is some human intervention.
Yeah, but the benefit is that in between we have this model, which model representing the system underneath. And the synchronization of the model and the system underneath, that's fully automated, based on test cases.
Second question, please.
Very short question. Could you please go one slide back just for a picture? Thank you.
Okay. I think you get the slides anyway, so
if I understood correctly, these active components are carrying their own knowledge about how this component, their physical twin, is working.
Right.
So that means that your knowledge is kind of distributed over all these different components.
Yes.
So is there any part of the system that has a global view, or do you have any vision of cross-component data analytics?
Interesting. You know my background is distributed systems. We don't believe in global views.
No, but those big data people, they would love to do correlation analysis about this component and stuff like that, but you distribute it, so you take that away. Is that by purpose, or?
Yeah, it is by purpose because the world is like that. And what I don't believe in is global control, centralized global control. But global views,
not controlling.
Sorry?
I'm talking about learning, about data mining on all these sensor data, and that occurs in all these different places to find correlations you haven't seen before.
Yeah. What you could do, I mean, my background very long ago was also databases. I mean, you could produce your own views of the system.
Okay.
You would define your own component, active component, collecting knowledge from whatever they like to, they have to decide. Yeah. And then deriving an abstract view as they like. But there's no general coordination of that. Okay. This is application specific. That's up to you. And this is done on purpose.
So that means that every change in the system that you are able to observe must be observable by single components. So you cannot observe anything which is just seen if you combine things.
Well, you can implement it if you're interested in that.
But right now how it is
but it's not provided.
The focus is single component change.
Right, yeah. Okay. We could provide the first level.
Okay, thank you.
May I add a question? Even if all of us are fans of distributed systems, I suppose it's very hard to ensure the alignment of between, for instance, you mentioned the business perspective, some technical perspectives, some engineering perspectives, how we could align this and bring this together even if we have no global model. I accept we are not catching and looking for a global model, but we have a sense of globality, and the question is, how can I understand as a software engineer too and a software architect a global aspect of an architecture coming from the integration of very different divergent things.
Well, you have interesting method in agent technology because you set your goals there. You could be setting technical goals, you could set economical goals, and they of course can be conflicting.
Yes, and my question is, what aid of an architecture we can provide to understand how this interaction, relationship looks like, and how we can provide a base, of course, even for big data analytics in this complicated field.
Yeah. Okay, this is very basic here. That's not our topic. This is yours. Maybe we could combine.
It's a question of another chair, perhaps, but it's a question for all of us.
Yeah. Just providing basic.
It's very interesting for discussion. Let's look again. Other questions? Yes, please.
For this approach, you need a very tight integration with the physical machines of rock. So my question is, do you think it's feasible to integrate this into an existing production environment, or only when you build new ones that design is driving?
No, that's actually what we do. We integrate existing environments. That's not quite true because we have toy environments, but like I said, they are asset. That's what they really have in their labs, these colleagues from production automation. But these systems exist, and we adapt to these systems. And they're nice demos. I mean, sometimes you have an existing system and you see the system move, the crane moves, things move. And right next to it, that's what we did for our first review. We have our screen showing what's representing in our agent system. And you can look at the screen and look at the physical system and compare whether it's correct or not. But of course, yes, we do adapt to existing systems.
So do you integrate at a very high level where you get, I don't know, a message bus or something, or do you have to integrate with individual sensors or things like that?
Well, we start at the lowest level, individual sensors, which we build into the system. That's what we are adding, which tell us like this part is moving from here to there. And then, I mean, looking at that, different time spans, and if it's on the conveyor belt and it's not moving, it's always on the same place, it's easy to say that may be something wrong. But that's right, correct, we added these sensors to existing systems.
So maybe I didn't get it correctly, but it's still on this toy level, you said. But is there a perspective to bring it soon in a real environment?
It's very close to real. Like, I don't know whether you know colleague Vogelhäuser in Munich, Technology of Munich. She has the biggest and largest, maybe most important chair for production automation. Yeah. And what they do and provide there is very close to reality, and she is a very close colleague in the same project. So it's not very far away from real systems. Okay. And they are larger, and the crane is not like this, but when we can make this either side. But the complexity is not necessarily, but depending on what you consider a system, and if you consider the production of a Daimler car or so, that's beyond. But it's basically producing parts for car production, these production systems. Or completely different areas, like filling Coca-Cola bottles. I mean, this is German, what's it called? SMEs, yeah, famous worldwide. And there are all kinds of applications, and they're not so complex.
Thanks again. I have to announce the finishing of our morning session now. So you have a lot of free time in the afternoon. I wish you a nice time and good discussions.
So they all have a local view of how much this mice stays in water correctly. And they learn if this is correct. Because someone who designed the system had put these compositions. The one from the frame, one from A, one from A. But there's no one who looks at the information. don't have this.